What is going on, guys? Welcome back to another video. In today's video, I am going to show you how to integrate the bell curve, which is what I have on the screen right now. This is pretty famous in terms of statistics. It is pretty much just a normal distribution, but it looks like a bell. I guess, I don't know, I don't see really a resemblance, but we're just gonna call it the bell curve. There we go. It's just, again, normal distribution. But first, let's get our facts straight. What is this function? Because obviously we have the mean to be the global maximum, but it kind of has like this limit and behavior towards zero. But like, what function is this? Well, here is where I introduce you two different types of normal distribution. We have the probability density function, or PDF, and the cumulative distribute function, which is CDF. So this, drum roll please, is, that's right, PDF. Okay, it's PDF. It's not CDF. Alright, let's just show you what CDF is, just for anybody who's wondering. So here is a CDF function right here. Let me just pull that up. This is a CDF function. As you can see, it kind of looks like a sigmoid type thing. I don't know. But that's not what we're integrating today, because this is a PDF. And now what is the PDF function? Well, it's this function right here. So yes, if you integrate this function, you will get this function, pretty much the area under the curve. So that's what we're going to do today. And yeah, let's get started. So first, I am going to start by copying this down here. And let us integrate this function. Alright. Now, we're going to do it by hand, obviously, because if you use Wolfram Alpha, pretty much defeats the point of this whole video. Just do it if you don't really care about how it works. But for those who care about how this works, stick around to find out, because we'll be using some pretty spicy techniques never seen before. Well, maybe. Okay, just me. Alright, first, we're going to take a look at how we can simplify this. Remember, sigma and mu are constants. Treat them like c's, or I don't know, whatever constant variable you call it. But again, it doesn't change. It's constant. So first, we're going to basically extract the bottom constant out, because again, just like pi, this sigma here is a definite constant. So we are going to pull that out. So that the bottom, we're going to pull the denominator to be sigma times the square root of 2 pi. And for the numerator, we have that pesky x variable in there, so we have to remain that. We have to remain this in the integral. So yeah, because we're integrating with respect to x, so yeah. So that is what we've done so far. Alright, now what? So now we are going to see if we can basically find a suitable u substitution value, because that's what we're doing for this. So you might want to just make this u, but think about this. What is the derivative of this function? Does it exist somewhere here? If not, then I reckon we don't mess with that. So we need to find another u value, but it is on the right track to think that the u is up here, because we're definitely not going to make this u, because that's just because e. Yeah, e isn't a good u value. So we're going to definitely make whatever this is a u value. So let's actually think about this for a second, what we can find for a u value. So let's start a new page here. So let's just work on this for a second. So just take that. Oh, accidentally erased that. There we go. There we go. So what can we do with this? First, let's just try to square it out. So squaring and multiplying, your basic algebra thing. The fraction remains, but this becomes mu squared, and then 2. Actually, wait, just sigma squared times 2, and the -1 goes to the top, so it's just negative whatever this is. So Pretty straightforward so far, nothing out of the ordinary. Now, well, what can we do with this? Because this still doesn't really seem all that well. So let's just change this, I guess, to this. Copy this whole thing, and we're gonna take this value, and we're gonna plug it here. So yeah, I mean, I don't see any difference. But now that we multiply this out, we can really change things up a little bit, because what we can do is we can actually set u to be somewhere in here, because we don't really want u to be a negative value. We just want u to be itself, like as it is. So the negative will be on the outside. So that just leaves with, again, this term right here. So what can we further reduce this term to? Well, we see that it's squared, so why not just take the square root of this? Alright, let me hold myself from getting too ahead of this. So let us just, I'm just going to do it, and now I'll explain what I'm doing. So if we're taking this, if we're letting u to be the square root of this term right here, then it will make sense that u will be, actually it will make sense that u squared will be this term. So far, I think so good. So again, let's set u squared this, and therefore u will be the square root of this term. So u is the square root. Before we calculate the square root, why are we doing this? Well, first of all, let us again ignore the negative, because we can't square root a negative. I don't want to go into the complex world. Let's leave that all behind. We're just going to stay in the real value coordinate system. So ignoring the negative, why are we even square rooting this? Because, you know, it's fine where it is. Well, that I will reveal later on in the video. But for now, you just got to trust me in square rooting this. Trust me, it all makes sense. But yeah, let's just try to square root this. So this square rooted just becomes x mu. There we go. And then bottom square root, based off of our exponent rules, square root of 2, and then sigma squared is just sigma. I mean, sigma square root is sigma. There you go. So this is the u value. Now, before we go back and substitute this in right here, we're going to basically try to find the derivative, because that's how u substitution works. So du, let's just put it in this way just so it's clear, extra clear. Let's extract. Can we extract the denominator out? Yes, we can. And then it's just x minus mu. So obviously this is very apparent that with this function being here, we can just remove this term, leaving this to be our slope. So that's just pretty much what it is. Now I'm just gonna change things up a little bit just to set up for my next thing here. So yeah, so that's kind of like the du right here. So now let's see if we have a du up here. Nope, we do not have a du, but we do have a dx. So why not solve for dx? So let us do this right here. Dx. Whoops, why did I use a fraction? Dx is just multiply this on both sides. So sigma square root of 2, and then du. There you go. So that is our u substitution complete. So okay, let's put this all back into one big u substitution thing. So again, just copy this thing, put that here. Alright, so again, u squared is this. Okay, so let's not even talk about u here. U squared is this. So therefore, this again, is u squared. So far, so good. Now, dx can't be, dx anymore. We have a u here. So what is dx again? Well, we solved it to be this. So again, I'm literally copy and pasting this just to see that nothing really disappeared or appeared out of, thin air. So yeah, that is pretty much our new integral right there. So it is starting to look like a function here. By the way, a pretty famous function, but again, we still really don't know what this is. Now, before you take this to the outside, I just want to tell you don't do that yet. So we're going to leave all of this behind and let us just focus on this integral because again, we already know what this is out here. So start new page, new equation. There we go. So this, now we have to really find what this is. So, alright, now I am going to do something completely out of the ordinary. So I want everyone to kind of listen and pay attention closely. We're going to try to morph this into another form without changing the value of it. And how do we do that? Well, we are going to multiply by 1. So let's actually just come in and paste this first. And we are pretty much, we're going to multiply by 1, but in a very specific form of 1, because 1 can be in a lot of forms. But for this form, I am going to specifically multiply by the square root of pi over the square root of pi. Now, this might seem so random, and can't spell here, but might seem again so random. Why are we even doing this? Why does the square root of pi have to do with anything? Well, for that, I think it is time for me to finally introduce you the error function. That's right, we're going to the non-elementary error function. Let me just show you right here. This is the error function. It's a pretty famous non-elementary function, which just means that you can't really prove it by representing it using any logarithms, exponents, polynomials, trigonometric functions. So we're just going to call it ERF because again, there's no other representation of this. So what we can do here is we can basically fit this into an error function. Actually, why is this so up here? Let me retype this. There we go. And the square root. Right. Then we, oh my goodness, let me just retype this. Square root and alright, so you can see there's a resemblance with this here and this. So this e to negative t squared is this e to negative u squared. But now what about this 2 over the square root of pi? Like, where is that coming in? Well, that's what we're doing here. We're multiplying by 1, or square root of pi over square root of pi, and we have this square root of 2. Now you can kind of see where we're going with this. But if you don't see it, let us do a rationalization of the square root of 2. Actually, well, let me rephrase this. De-rationalization or your rationalization, I don't know if that's even a thing, but we're actually taking the square root of 2 and we're actually, unrationalizing it. We're actually changing it to its unrationalized form. So let us see how we can do that. So square root of 2, again, we're going to unrationalize it. So we're going to actually put the radical in the denominator. So this will be 2 times the square root of 2. Again, pretty basic de-rationalization or your rationalization. I don't know if this is even a thing, but it definitely is in terms of math. We can definitely do this. So, yeah, so that's pretty much what we just did. So, okay, so now let's go back to the error function. Alright, so we do have a 2 on the numerator, but we have a square root of 2 in the denominator, so that's kind of bad here. So, what can we do now? Well, first, what we can do is we can, okay, let's move the sigma out because we don't really care about the sigma. So let's move the sigma out. Again, I am, for some of you who have done this before, this might be extremely apparent, but for those who haven't, I am doing it one step at a time just so you know what we're doing here. So again, this sigma is now out here because again, we don't really need that right there. Now, what we need to do is we need to basically multiply this by 2. So let us put this up here. Actually, wait, let me just start a new one. Again, we're taking it one step at a time, even though if it requires extra space here. But this is just this. Let me copy that. And then we're going to put this right here. So we have, again, hopefully you can follow this line of reasoning and you see that we just, again, modified a bunch of these terms right here, but we haven't really changed anything from here. So this does in fact equal this if you really take the time to simplify this. Okay, now what we need to do is we need to basically take this this square root of pi here, this numerator, and we're going to put this out here. So again, let us copy this first, and then I'll show you what I mean. So this right here, we're going to take that out, just, yep, and then we're going to multiply it by sigma, which is already out. And then what we're going to do is we are going to take this square root of 2, we're going to take that out, and we're going to divide it because, again, it's in the denominator. So there we go. There we go. So now we can simplify this. Let's move this square root pi over here. Well, not there. Here. And remove that, whatever that is. So now we have this new form. Hopefully that was, apparent, because this is pretty much the most crucial step of all. Now, again, do not take this square root of pi out. We need this inside because what we can do is, if you want to, don't cancel out these, because if you cancel out these, we won't get the error function up here. So again, this 3 lines of math is the most crucial most crucial step in differentiating the bell curve, or integrating the bell curve. I don't even know what I'm saying anymore. Again, we're integrating, not differentiating. Okay, just get that clear. I don't know, my head is pretty much broken. Well, actually, I don't know. Anyways, let's just continue. So now what we can do is we have this constant and this constant right here. So I think this is where the pretty much eureka moment comes to most people, is let's copy this right here because they're equal, and let's add in parentheses here, and let's take this and this out. So this, where am I looking at? Okay, 2 square root pi. Okay, that disappears. That disappears to become this. And would you look at that? This and this. Okay, ignoring the definite bounds here, because that's what we're trying to do here. But that is pretty much, this is the error function. So we have done it. We have successfully transformed this u substitution thing to a error function with u inside. Yes, there we go. So wow, that was pretty good. Now we are done with our u substitution. Now let's put it back here. So This, again, this becomes this, okay? This integral is gone. It's no more. It will be replaced by this. Now here is where the fun truly begins. Look at this. So, let's just change this a bit. Square root pi. So this, or should I say this, and this cancel out. Right? So that's gone. So now that just leaves with 1 times the square root of 2 times the square root of 2 times ERF of u. And what is this? Okay, that's just 2, right? So, therefore, we have our final answer right here to be equals. So again, this is just 1/2. So 1/2 times ERF. Now, what is u here? Well, u is, what is this? It is this right here. So let us substitute u back in. And then, obviously, the last part to solve the integral, to finish the integral, plus c. And let's see if we can highlight this. Actually, no, I don't want to. And we are done. That is, in fact, the antiderivative of this function right here. Man, that was a heck of a journey. Look at this. I don't even know what to say. I mean, I definitely am not the first person to think of this method, but I just want to basically let everyone know how this is done. So to recap, we pull the constants out, find a suitable u substitution to fit our error function here, and then we suddenly multiply by the square root of pi over the square root of pi just to get it in, and then we irrationalize this from basically the square root of 2 to 2 over the square root of 2, and then we move all the constants out except for 2 and the square root of pi, and then therefore we can get this term, and then we get the error function, and then plug that back in. This becomes 2, and finally we get this as the answer. Alright guys, thank you for watching my video. I might make more of these integration videos if this gets received well. But anyways, thanks for watching, and I'll see you in the next one. Peace.